Good evening, everyone. Today's class is on failure of materials in engineering systems. In this class, we look at mainly mechanical failures. The learning objectives for this session is the meaning of failure of components. When we say components or systems fail, what is the actual meaning of that? What are the different types of failures? And how are they caused? We'll look at some specific principles and some generic root causes behind this. That means what are different types of failures? And the main focus here is on mechanical failure. There are many types of failures. This class mainly focuses on failures of mechanical systems and components. So what is the definition of failure in this context? Whenever you say there is a failure, what is the meaning? Its meaning is this. It can be defined as an inability to perform. So when you say it is not able to perform, that inability to perform has to be quantified. You cannot say it is not performing. You have to say it is inability to perform to a particular level. So at a specified level. So if you put together, it is like this. All kind of failures are treated as not able to perform at a specified level. This can apply to individual parts. It can apply to a whole machinery. It can also apply to systems. And the same definition applies in non-engineering areas also. For every kind of system procedure, there is a requirement that the procedure should lead to some performance. And if that performance is not achieved, then you will say that the procedure also has failed. This is a generic and useful definition. It can be used everywhere. In the context of our discussion, we'll be looking at this. So if you take an example that if you say the auxiliary engine of your vessel is failed, it is not performing, what are the different levels of failure? One will be that it cannot be even started. That you try to start, it is not starting, or it has got such a major defect that it cannot be run at all. So that engine is not even able to run or do anything at all. That is one level of failure. Second level of failure will be it can run, but it cannot take the full kilowatt. If it is designed to be designed to supply power for 700 kilowatt, then it is not able to develop 700 kilowatt power. So then we say it cannot take the specified load. This is an example of a failure. So this is a different level, but it's still failure. One more example will be it can take full load. It is capable of developing 700 kilowatt, but the consumption of fuel or the consumption of lube oil is excessive. This also will be considered as a failure, but it's of a different level. And all of them have different consequences. Then a very severe failure can be like this, that if you want to stop, it cannot be stopped. If running machinery cannot be stopped, that can also lead to serious failures, especially for a main engine and lifting gears. And all these kind of machinery, if they are not stopped, when they are required to be stopped, that can also result in serious accidents or failures. So this, as an example, failure can be of different types, and it can also be of different levels. Now, if you think of a low lube oil pressure trip for an engine or a turbine, then what will be the meaning of failure here? Can one of the students answer this? What is the meaning of saying the low lube pressure trip is failed? Please answer one at a time. Yeah.
Trip doesn't work. It concerns about the safety of the engine, and trip doesn't work.
Yeah. When you say trip does not work, that is a general word, does not work. So, but what is the meaning of saying it is not working? Is there only one way it will not work, or are there different ways it will not work? We're not talking about the reason for it not working. What is the normal understanding of saying the low lube oil pressure trip is not working? Okay. Sound is not clear. Okay, I will answer this. So one way of failure is that the lube oil pressure goes down and it goes to a dangerous level, and the trip is still not stopped the engine or the turbine. This is one type of failure, that the low lube oil pressure trip is failed, we'll say, when the pressure is gone down, but still the engine is allowed to keep running. But there is one more type of failure. That type of failure is when the lube oil pressure may be all right, but the trip activates and it stops the engine. Will that be also considered as a failure?
Yes. Yes.
That is also a failure. Now, out of these two failures, which is a more serious failure?
The first one.
First one. Yes. What is the reason?
Chances of engine getting damaged. Probability is more actually.
There is a definitely there is a chance of failure to the engine. Engine will get damaged. But in the other case, where with the oil pressure being normal, the engine is stopped. Will that also lead to some failure? Will that lead to a consequence?
Yes, it depends on situation, which vessel in maneuvering or restricted waters.
True. So it means that even with a normal lube oil pressure, the engine is stopped. So if that is the case, then when you want the engine is not available. But depending on where the vessel is at that time, this can lead to further damages, or it may not cause any damage at all. So the vessel is in open sea and no traffic in deep water, and if the engine stops, it will not lead to any major consequence. But if this happens during maneuvering time or when you are close to land or in heavy traffic, in such cases, definitely it can have a serious consequence. So the idea is that one type of failure where normal lube oil pressure is there, but the engine is stopped. That is also a failure, but usually that is of a lesser consequence. But the other one will always lead to serious damage. It doesn't matter whether you are in open sea or whether you are in maneuvering condition. Either case, the engine will be damaged. So for every kind of equipment, there are different ways of failure. So that has to be understood first. What is the meaning of failure? So both these types of failures are not equally important. You can say the probabilities of further damage are different for each of this. Next case, you think of brake in any kind of vehicle, or brakes in lifting gear, for example, like you have in cranes or other systems. What is the function of brake? Brakes prevent movement, or they bring moving parts to a stop. So are there when you say a brake is failed, what is the meaning of that?
It is not releasing, but in the other case, it is not holding.
So one way of brake is failing is that when you are applying the brake, it is not engaging, it is not holding. And the second type of failure is when you want to release the brake, it is not releasing. That is also a failure. In most cases, it is the first one which is more dangerous. When you want to stop and it is not stopping because of the failure of the brake. So here again, you'll see there are two different ways it can fail. You think of valves again. Valves also can fail in different ways. One is a valve which you want to open is not opening, or second is when you want to close, it is not closing, or if it is closing, it is not closing fully. In this case also, the failure to close is often the more serious consequence. It has more serious consequence. So in every kind of component design, one of the first principles you see is what is the purpose of this component, what are the different ways it can fail, and which is the more dangerous or the failure which has more serious consequences. That is what has to be understood first. And based on that, the system design is carried. So there is something called failure mode in any kind of system. Again, our discussion is mainly on mechanical systems. So what is the meaning of failure mode? So when you say failure mode, it means what went wrong in this part. That is the meaning of what went wrong is the meaning of mode. So it will be something like a rope parted. If you say that is how that is what went wrong in this. When you say failure mechanism, the word is for what is the reason for the failure. That how did the failure take place? So in first is what went wrong. Second is the cause. So if you see a few examples, mode is the proximate cause. We say proximate cause is that this is what actually happened, and then the mechanism is more like the root cause, which comes much further down. Mode will be more specific to that particular application, but mechanism will be more generic. So if you see an example, a wire parted, it can be a lifting wire in a crane or a wire sling while lifting something. Then that is a failure mode. That parting of the wire is called as a failure mode. It can be a mooring rope as well. Then what is the reason for this failure? One reason is overload. That the wire rope was overloaded, and because of the overload, the rope parted. So that overloading is called as a mechanism. This is a difference between what is called as mode and what is called as mechanism. There are different books which will not discuss this difference in too much fine. Like it will be the same word will be used in interchangeable way. But generally, this is the understanding that modes and mechanism means different things, slightly different. So we'll be looking at these kind of modes. How do they fail? So if you say something which is moving, which is required to move, a shaft which needs to rotate, or a piston which needs to reciprocate inside a liner. If these parts do not move, then that is one type of failure that is called a seizure. So which can happen with pumps, which can happen with other kind of drives. It can happen even with engines. So the piston is seizing inside the liner is an example, or a bearing or a pump shaft is not able to rotate at all. Then we say it is seized. So that is one type of failure. Then there are different types of fractures. Fracture means a part is broken. It has come apart. That something is broken in that part. That is called as a fracture. And there are generally three types of fractures. One is called ductile fracture, other is called brittle fracture, and the third is called as a fatigue fracture. So there are three different types of fractures. We'll be looking at these in greater detail. Then example of what is called as buckling. Buckling is a type of failure which takes place under compressive load. When the load is compressive, the component is put under compressive load, you have failure called buckling. Then you have failures which are examples of plastic deformation, or we say the component is yielded. Everyone understands the difference between elastic deformation and plastic deformation. What is the meaning of elastic deformation?
Stress proportional to strain, and it will come back to its original position once the force is removed.
Once the force is removed or once the stress is relieved, then the component should come back to its original position. And this is the most common example of deformation. So every mechanical component, while it is in use or while the part is assembled, will definitely undergo some deformation. So if you have a flange and you put nut and bolt and you tighten the bolts in the nut and if you tighten the nut and bolt, then the bolt will stretch. But there is nothing wrong in that, because once the bolt is loosened, it will again go back to its original length. That is called as elastic deformation. Plastic deformation is when it is permanently changed. Either its length is changed or section is changed. That is called as plastic deformation. So the idea is that you can have deformation without fracture. The part may not break apart, but it is gone beyond its limit. That is the meaning of plastic deformation. This is also a mode of failure. You can also have excessive deflection. Now this deflection can be entirely within the elastic limit. In the meaning that it can, if the force is released, it can come back to its original position and size. But the movement is too much. The deflection can be excessive. This is also a type of failure. So we are mainly looking at these kind of failures first. There are others which will continue, which is more about how parts wear down, and because the parts wear down, the sealing failure takes place. They are all additional types. But this class is mainly focusing on these types of failures. So what are the mechanisms by which this can happen? Number one is excessive stress. That the stress becomes too much, beyond the ability of the mechanism to, or beyond the ability of the component to take. That is called overstress. It can be because of fatigue. Fatigue is a principle which is known well. The issue with fatigue is that you have stress, but the stress is not constant. It is varying stress. So this excess fatigue can be from two parts. Either the stress is too high, or the duration for which the stress reversals are taking place, that is too high. So you have either excessive stress or you have fatigue for prolonged duration. Either way, fatigue can lead to failures. There are many examples. Corrosion is another example of failure. How these parts, normally corrosion leads to further mechanical failure. It can even lead to fracture. Wear down is another example. Wear down will again reduce sizes. Erosion is another size. So the difference between the previous slide and this slide is, you can see. So when you say there is a fracture is a mode, that fracture can be because of these kind of reasons. That a part fractured because it has got corroded and it become less. It's a very common example, especially with hull structures. So the deck developed a crack. The deck developed a crack because due to corrosion it became very thin. So this is the mechanism, and crack or fracture is the mode. You can also have failure due to this erosion, or you can have due to fretting. Now, fretting is an example of wear down at assembled parts which are assembled together and which should not move relative to each other. If these parts are moving, then we say there is fretting, and fretting will result in loss of material, and that will also lead to failures. Now, this picture you see is an example of buckling. Now, this is a bent connecting rod in a small engine, like an automobile engine, and this is due to excessive compressive load. That the compressive load is too much, and due to this, the component is failed. So the connecting rod, instead of being straight, is bent. So you say you've got a bent connecting rod, and that has happened because of what is called as buckling. And in this example, this buckling is due to hydraulic lock. And hydraulic lock is you have to understand why the hydraulic lock happened. You have to understand why did it bend in this particular direction. When you say it is bending in this direction, why did it bend in this particular direction? That reason you will see as it comes. Now there is a formula for understanding how buckling takes place. If you have a column or what we call as a strut, which is a elongated part, and from both ends you are applying compressive load. So what is the maximum compressive load the part can withstand without buckling? That is given by this formula. This is not the stress value, this is the force in Newton. So in Newton, what is the maximum force it can withstand in this direction, axial direction? That is given by this formula. In this formula, you can see the letter E stands for modulus of elasticity. The letter stands, I is the second moment of the cross-sectional area, or whichever is the lower cross-sectional area. And L is the length of the column. That whatever is the length of the column, that is taken as L in this formula. Pi is pi, that everyone knows. And K is called as the effective length factor. This is an important point to understand. This is called effective length factor. So that's a number which has to come in the calculation. And remember, it is coming in the denominator. So the lower this value is, it means more load can be taken by the column. So the lower the denominator value is, the load which can be taken by the column will be higher. Now this K value varies with the type of fixing. So if both ends are rigidly fixed, both ends of the columns are rigidly fixed, they cannot move sideways, they cannot rotate. If it is rigid, both are rigidly fixed, then the number taken for this is around 0.65. Theoretical value is around 0.5, but practically it is normally taken around 0.65. That is the number taken for K. Now, if both these ends are hinged, both ends are hinged means they have freedom to turn like this. And the connecting rod is a good example. Upper end of the connecting rod has got a gudgeon pin. Bottom end of the connecting rod has got the crank pin. And both these are hinge joints in the sense that the tip of the rod is capable of rotating. So in such case, this number becomes 1. And in the third example is if the end can even move laterally. If it is capable of moving laterally, then this number becomes even more. That there is no fixture on the side. If it is capable of moving like sideways, then the number becomes even higher. So the point is, the higher this value of K, this lower is the value of the force that can be taken. Now, one of the important principles you will understand here is when a component is put under tension and it is put under compression, behavior is not the same. There are a lot of differences. In the case of compression, length of the column will matter. In the case of if the same thing is under tension, it does not matter at all. If you are putting a component under tension, what is the formula for the stress? If something is put under tension, what is the formula for stress? You take a component like this and you pull it apart like this. And what is the formula for the stress? Can one of the students answer?
Load by area.
It is the applied load divided by the cross-sectional area. And according to the stress, you will get a certain value of strain. And as the stress becomes more and more, it will go to a level where yielding will take place, plastic deformation starts, and finally it will go to a level where fracture can take. And you will see the entire calculation, length does not come at all. So in the case of a component under tension, length of the part does not matter. What matters is only the cross-section area. Whereas in this case, you will see length also matters in compression. Second important principle is, in the case of tension, only the cross-sectional area matters. The more cross-sectional area you have, the component can withstand more tension. But in the case of the compression, what matters is the second moment of area, not the area alone. It is the second moment of the area. Second moment of cross-section means you should look at your I value. So it is not the value of the area alone, but where is the area distributed. That is how it matters. You will see very commonly connecting rods are made in I section. Right? A lot of engine connecting rods you will see. Most trunk piston designs, they all have an I section. What is the reason for having an I section? Is because the second moment will be more. You can increase the second moment of area by using an I section. So if you look at the way tensile stress leads to failure, it is like this. Tensile stress increases, it will lead to a yielding level, then it goes to plastic deformation, and then it causes a fracture. But in the case of compressive load, it can cause buckling even before plastic deformation takes place. So plastic deformation means the part will not get smaller, or the length will not reduce. Even before the length reduces, the buckling can take place. So for any kind of compressive load, the most important failure mode is buckling. We'll see one more example. This is a very severe accident which took place in a vessel on a passenger ship named Carnival Splendor. If you go through the full accident report, you can see the full details of how it happened. So that vessel, there was no mechanism of blowing through these engines. These are generators, but with electric propulsion, that is also the main engine. So you have to understand that. So what happened is there is no practice of blowing through the engine. Water from the scavenger cooler entered the cylinder because of a leakage. That scavenger cooler developed leakage and water entered inside. And due to this water ingress, when the engine was started, the connecting rod bent due to hydraulic lock. Now, even though the connecting rod bent, engine was still running. Engineers were not aware that the connecting rod is bent. And the engine was running, and because of the bend, the stress on the connecting rod, stress in this part increased. Now this additional plating you see is what was welded to hold it together, to make it, when the examination of this component was done, these parts were welded, these plates were welded together to make it look complete. So this part of the connecting rod developed the cracks, like the surface stress increased in the bent portion, and from that surface stress, fatigue failure result. So fatigue started from here and then moved towards the center, and it failed. Parts came apart, connecting rod failed, counterweights failed, and the parts of the rotating parts were thrown out. It created a large fire in the engine room and severe consequences, a lot of losses. Do you have any questions up to here about the importance of buckling, and especially as a column? Then the other types of failure, if you go to failures of parts otherwise, there is one type of failure called ductile failure. Ductile failure will be starting with elongation, that the part will elongate. There will be necking. Necking means there will be reduction in the cross-sectional area, and you will see a very clear shape here, like you see a shape called cup and cone shape is commonly seen. So this is the cup part. This is the cup part, and this is the cone part. So there is quite a bit of narrowing down, and then it fails. Now this is a very common type of failure in elastic materials, or materials which are ductile, mild steel or low carbon steel, as an example. They are ductile materials. So what will happen is that before they break apart, it will stretch, and often it can give some warning because of this. And to prevent ductile fracture, what is important is if you are thinking about the materials property, what is important is the UTS value of the material and also the yield stress value of the material. So you must select material with the correct yield stress according to the load that is being applied on the component. If they are brittle fractures, then they look very different, because in the brittle fracture there will be hardly any elongation. If you are thinking of tension, there is hardly any elongation will be there. There will be no narrowing down or necking. And if you put the parts together, it will have the same shape and will also have the same size, because there will be no plastic deformation. So even after the fracture, if the parts are put together, their size and shape will be same. So examples are all this ceramic, glass, cast iron. All these are examples of brittle fracture. So you know that if a ceramic cup is broken, then we can if you can get all the parts and if you stick it together, it look like original because there is no deformation. There's no plastic deformation. It retains the shape, the size. So for brittle material, cast iron is the best example, or high carbon steels with high carbon content, tool steels. They are all brittle materials. And brittle material, if they fail, their fracture will look like this. And even ductile material can become brittle at low temperature. This is one of the important principles to keep in mind. So that is why, depending on the application, you will have to have material which can withstand low temperature. For shipboard, liquefied gas tankers, especially LNG tankers, and few other refrigerated gas tankers, they give the best example that because of the low temperature of the cargo, you need to select material which will not become brittle. Otherwise, they will not be able to withstand any impact. So, in the case of brittle failure, or if you want to prevent brittle failure, then the most important principle is called toughness. Now, toughness is different from strength. Strength is measured by UTS or by Young's modulus. Toughness is measured by the amount of energy which is required to break a part. And many of you will remember there are this impact testing. ISO impact test is there. Sharpie Win-Notch test is there. What is the output of this test? When you say I do a Sharpie Win-Notch test or ISO impact test, what will be the result? Like, how is toughness measured? Toughness is measured by the amount of energy required to break this specimen. You will remember in your college days that in impact testing, a specimen is made. The specimen is broken by hitting it with a hammer. Then the amount of energy required to break that specimen is the way this toughness is measured. And the tougher the material, it will take more energy to break. So toughness is a combination of both tensile strength as well as ductility. So if you don't have enough ductility, then it will be brittle and it will not be tough. That is the difference. Then if you look at fatigue fracture, no, fatigue fractures are different from other type of fractures. The fatigue has happened because of repetitive stress. And a component which is failed due to fatigue, the fractured portion looks very different from all the others. If you see, there will be hardly any elongation, provided the stress is kept within normal limits. So the elongation will be less, but the fractured surface will not be uniform. You will see distinct areas, like one part of the fractured surface looks different from the other part. So there's always some kind of a fracture or crack initiation point will be there. And very often they come from surface, not all the time, but if the inside part of the component has some defects like a blowhole or any such defect like that, discontinuity is there inside, then it can start from there also. But very often it starts from other parts, from the initiation part. So this in this example, you can see this is the keyway, and from the top of this keyway, it is starting from here. Crack is started here, and in this case, it is started from somewhere here. And so the failure starts from there, and then it progresses. So this portion where this crack, what is started from here is moving till here. These portions are called as beach mark. You can see like slight wavy marks are there. This is similar to the sand mark you will see in beaches. That is why it is called beach mark. This one, all these examples. So these are all examples where the failure started. So in this case, the failure starts from here, right? Failure crack started from here. The initiation was here, and it starts moving like this, and then finally, at one point, it will break. So where the initial part is there, it will be smooth. All this part, it will be smooth, and then finally, where it breaks, the whole part breaks. This part will be rough. So very often you will find that where a fatigue fracture has taken place, the shape will be very different. This is a very clear-cut indication that this failure has been caused by fatigue. And you will not see that cone and cup type of shape. You will not notice any necking. So the ability of a component to withstand fatigue is defined by something else. You cannot do it by the normal tensile stress curve. So this is by this well-known curve called the SN curve. Now in the SN curve, you have stress levels on the y-axis here, and number of stress reversals to cause failure will be on the x-axis here. So it says this is number of 10 raised to 3 means at 1000, like this. So so this value will depend on RPM, and it will also depend on number of hours. So higher the RPM with less number of hours, you will be reaching this. So what is happening in this graph is that when the stress levels are high, then failure can happen at even lower number of cycles. Like even after one or 10,000 reversals, this can happen. Failure can take place at this kind of stress. But as the stress is brought down, the number of reversals to cause failure will keep on increasing. And finally, it becomes flat here. So as the stress level is going lower, it will become flat. So if you have most ferrous material, it will be like this. They tend to flatten out, and where it tends to flatten out, it means beyond this, actually quite a long lifetime available for the material equipment. So this stress level here, where this line is flattening out, this is called as endurance limit. Now, for a non-ferrous material, it does not flatten out so much. This is B is for non-ferrous material. So since it is not really flattening out, for this material, you should also specify by some number of reversals. So it will be like 10 raised to 7 reversals, 10 raised to 8 reversals. Depending on the RPM, it will reflect as so many number of hours. So the meaning of this is, if I am designing a component which has to withstand fatigue, then I have to look at this figure. The actual stress value has to be brought below this endurance limit. So how do you do this? How do you bring down the actual stress below allowed values? It is like this. It is based on these factors. So you have this number called factor of safety. This factor of safety is a ratio between the ultimate stress and the maximum working stress. Now, if the ultimate stress is UTS value is 420, and then or 400, then if you apply a factor of safety of 4, that means the maximum working stress will be brought below 400. That is the meaning of factor of safety. It can also be made as a ratio between yield stress and maximum working stress. Now, depending on what is the mechanism that is used, it depends on what is the type of material, whether it is a ductile material or whether it is a not so brittle material. Different values are used for factor of safety. So higher the factor of safety, it means the maximum working stress will be at a lower value. So between the UTS and the maximum stress is what is used for common for brittle material and for any kind of impact loads. Or it can be between yield stress and maximum working stress. And this is more common for ductile material. Higher the value of factor of safety, the maximum working stress will be lower, which actually means the components will be bigger. And you have to select the correct factor of safety in designing. So what is important is that the engineer who is operating machinery, looking at equipment, we should also be aware of what is the factor of safety involved in the design. So we must understand that different type of equipments are designed with different amounts of factor of safety. It is not a fixed value. It varies from different type of equipment to different type, and also depends on the type of loading. So there is like all equipment do not have the same safety margin. So the important principle is something like this. If you have a static load and on ductile material, static load means the force is fixed. So some part which does not move at all is bolted down. Like you have an example like a pump is tightened down or an air bottle is tightened down, like so, or a nut and bolt is fitted. So the load on this part will be fixed. For that, the factor of safety can be only around 2. If the factor of safety is 2, it means from the maximum ultimate tensile stress, you have brought down the actual stress to just half of that. So for a cyclic load, the factor of safety will increase. When it is alternating means between tensile and compressive, the factor of safety can go up to 8. If you have sudden loads, then it can go up to 16. And in brittle material, they will have higher factor of safety when compared to ductile material. So it is mainly these two principles. Are you looking at a brittle or ductile material? And then what kind of load is there? Is the load static or is it going to be changing? Or is it going to be a sudden impact load? And the highest factor of safety is for sudden impact loads. What are the other factors which will be considered is operating environment. Is there corrosion in the system or the temperature is high? How easy is it to look at the component? How critical is the component? These are all other factors which will be considered. So if you look at this, now if you can understand, this is the UTS value. So if I have a factor of safety of 2, that means the working stress will be here. If I use a factor of safety of 8, I have brought the working stress here. So it will be operating only at this level, and ideally there should be no chance of failure. Then why is it that components still fail? Components which are supposed to be built with so much of safety, why do they still fail? That is because of, very often it is because of unexpected sudden load. That it is not designed to withstand sudden loads. So in general, it is supposed to be having static load or gradually increasing load. So what are different ways sudden load can come? One is pressure surge in pipelines, is an example. So if valves are closed suddenly or valves are open suddenly, you will get pressure surge in pipelines. You will have water hammer in steam lines. This will lead to sudden impact loads. And moved vessels, vessels which are tied up, if they move suddenly, the ropes will come under very severe stress. So the problem with all these kind of sudden loads is that kinetic energy in the water or kinetic energy in the liquid or the kinetic energy in the vessel, it will turn into work on the component and it can cause very severe damage. Other factors which affect corrosion. Corrosion and fatigue is a very, very dangerous combination. There are a lot of examples of failures, including in cylinder head studs of engines, where corrosive atmosphere is there and the load is a changing load. Erosion has caused failures. Wear down has caused failures. and fretting in assembled parts. All these are operational factors. So the important thing for the engineer to understand is this. Number one, depending on the type of material and the type of load, components are built with certain amount of factor of safety. But that alone doesn't guarantee there will be no failure, because there are other factors. Most important is the way you can overload components without understanding that you are overloading. And you can also have examples of fretting and vibration. You can have examples of vibration in pipes, which has caused serious accidents. Wire rope and mooring rope, as an example. Even ropes in good condition can fail because of sudden movement. It can happen due to the rope, the vessel is moving high due to change in draft or tide change. So how should you take care of this is, the relief valve in your hydraulic system should be set correctly so that it is not possible to overload the rope. And if the ropes are on drums, the brake should be set correctly, that it is not overloaded. Another very, very important principle is in lifting gear. Lifting gear is for lifting, and they are not meant to be used for pulling anything. That's an important principle you have to understand. And then you should know whatever weight you are lifting, you should know the weight. And then rigging arrangement will always change the load. So if you see this example, the load is only 1 ton. There are 2 ropes which are used for lifting this 1 ton load. If the ropes are arranged like this, then each rope will be having only around half a ton. That means it is equally shared, almost. If this wire sling is shorter, if this sling which is holding it together, if they are shorter slings, then it will have to come like this, and this angle increases to 60, and the stress will become, and the load becomes 0.6 almost. Then with the shorter and shorter sling, if it comes like this, finally you will see at 120 degrees, each of this rope is actually carrying 1 ton load. And if you have something like this, and you're going to carry from here in the center, then each of this rope is actually carrying 6 tons of load. To carry 1 ton of weight, each of this rope is loaded to 6 tons. So if you are putting a strap around the load, often you'll say that I'll put a wire rope around the load and lift it, then it can become very similar to this arrangement, which is at the lowermost. So the point is that you may be thinking that I'm lifting only a 1 ton load, but you can end up overloading the ropes because of the way the rope is arranged. So normally the guideline is the angle should not increase more than 60. This is the normal guideline. So anywhere like this is you are going to be overloading the rope. So these are the main principles of fractures and how they can take place. Other important failure mode is seizure of parts. So seizure takes place due to failure in lubrication. It can happen due to bearing damage. It can happen due to overloading of parts. It also happens due to overheating. So what are the different ways you can prevent these things? Examples of piston seizure, shaft seizure, all these are examples. So how do you prevent seizure? First of all, do not overload, whether it is your engine or whether any other part, do not overload. So as an engine is, especially generator engine, if it is made to carry more and more kilowatt, then the amount of fuel burnt in the cylinder becomes more and more, and the heat releases more and more, and the piston will expand more, and the lubrication with the cylinder liner becomes less, and they are seriously risking a seizure there. It can happen with other parts also, even with bearings. Control the temperature, don't allow the temperature to become excessive. Ensure correct lubrication is maintained. And for rolling contact bearings, monitor vibration so that this failure of the bearings can be prevented. So these are a few examples of how mechanical components will suffer failures. and what are the ways you must take care.